Hi, I'm Sarah Black. I just finished my third year of my PhD here at CU. I'm in the geology department, and I study hydrothermal alteration in Costa Rica and Iceland as analogs for Mars. So planetary science and Mars. So first things today, I wanted to start talking about Pluto and Charon. If you have been paying at all attention to the news in the past year, you've probably heard something about these. Up until July of last year, the most we knew about Pluto and Charon was that they were out there, and that was really it. The best images we had were like a couple pixels across from Hubble, and that was all we knew. We expected that Pluto and Charon would be these really cold, icy bodies that were just covered in craters, geologically dead, and not really much interesting to look at there. But as we have learned over the last several years of space exploration, we at least expected to be surprised in this case, and it turned out we were surprised. So these are our newer images of Pluto and Charon, much better than the couple pixels that we had before. So the large one here is Pluto, and then that one up there is Charon, the moon. It's a binary system, so they're orbiting together like that. And in July 2015 of last year, we had our closest approach of the New Horizons mission, which took outstanding data, and we're still getting data back. It takes about 16 months with the data rate, the data download rate that we have. So at this point, we really only have a fraction of the data that we're getting back from this mission. So there are new interesting things to come in the future. So I just wanted to do a quick overview of some of the interesting things that we've seen at Pluto and Charon, starting with, we expected this place to be geologically dead, more or less. And if you are familiar with geology principles, the older a surface is, the more craters it will have. So when we have this is one of the high-res images of Pluto. This is Sputnik Planum, the bright side of the heart. And on Sputnik Planum, there's no craters at all, which means that this is actually something that still has some kind of active resurfacing or very recent resurfacing process going on. It's a very young surface. We did not expect to see this. So the surface of Pluto could potentially still be actively resurfacing itself and doing things instead of just sitting there and getting hit with meteors. We also, on Charon, you can see going across right here, there's this huge canyon system, and this is just a zoomed in section of it. This is Serenity Chasma, it's been named. And there's a humongous canyon system on Charon, which has some kind of implications about Charon's cooling and expanding history, which you'll hear more about later this afternoon. We also saw signatures of methane, ammonia, carbon dioxide, and water ices on the surface. We can look at the type of light that is reflected off of a surface and look at the wavelengths and determine what the composition is of that surface. And you can see that we have several areas. It's not homogeneous. So the surface of, this is of Pluto, this right here is the bright part of that heart there. And the surface of Pluto is not homogeneous. It has areas that are more methane rich or more water ice rich or more CO2 rich. So this has implications for the geologic history of this area and how these materials became segregated into different locations on this planet. Don't really want to call it a planet and get in trouble. But you know what? It's Pluto. All right. And the other thing that we found that got a lot of people excited, myself included, because I'm a volcanologist, is things like this down here, zoomed in, that look like they could potentially be cryovolcanoes or ice volcanism on the surface of Pluto. So Pluto and Charon, a lot cooler than we thought they might be. So moving quickly to Venus, you'll hear a little bit about Venus today as well. Venus has a really thick carbon dioxide atmosphere, makes it really difficult to do geology there because we can't see through it. But we really like to look at the atmosphere of Venus because that in itself is pretty interesting as well. So astrobiology, you guys probably all know about the habitable zone. So Venus is right here, kind of on the edge of the habitable zone in our solar system. And so if life ever arose on the surface of Venus, which could possibly have happened, maybe it actually then migrated to the atmosphere. So I really want to get one of those things. So maybe life migrated to the atmosphere of Venus. So people like looking at the composition, the structure of Venus's atmosphere to try to figure out, is it possible that things could be living there? Where could they be living? How could they be living there? What could they be doing? How did they get there? And of course, moving on to Mars, because we have a whole Mars session. So if you haven't heard, NASA's mission objective with Mars is follow the water. So everything that we are doing right now for Mars exploration somehow ties back to water. So first off, we like looking at the geology of Mars. And things that we've found so far in this follow the water theme, we've found signals of aqueous alteration, so alteration by water. This here is an XRD, an X-ray diffraction pattern. You don't have to worry about the instrument. It just tells you what types of minerals, what types of materials are present in this rock that you're analyzing. And this XRD pattern right here is from the Sheepbed Mudstone in Gale Crater, or the Curiosity rover. And this has actually, in here, don't worry about where, but in here, this shows you the signal of clays and amorphous materials in these rocks and soils. And clays and amorphous materials are good indicators of aqueous history in that region. We've also, from orbit, we can identify minerals. That same thing with Pluto, looking at the reflected light off of a surface. And we've identified salts. This bright green area here is an area of a salt deposit in a crater on Mars. Salts can come from evaporating liquids. So this area here, there's also all these little blue lines around the edges are things that look like fluvial or river network systems, and they all go into that crater. So that was potentially an old lake that then dried up and left these salt deposits behind in the rock record. So we also like to look at characterizing the climate of Mars, and in a little bit you'll hear some stuff about some climate modeling. So we see all these geologic signals that there was water on Mars in the past. There's that theory of a warm, wet, early Mars. But Mars climate modelers keep coming back at us and saying, we cannot get this model to work. It doesn't work. So there's a lot of challenges when it comes to modeling climates, Earth or Mars, doesn't matter. A lot of challenges when it comes to this. There's a lot of variables, and trying to make all of these things fit together in a way that gives us the most accurate representation of a climate in the future or in the past. So there's many, many variables. One of the things you'll be hearing about is micrometeorites. The other thing, it's astrobiology. So of course, we want to determine if life ever arose on Mars. And there's several different things that we're looking at in this field here. One of them is looking at alternative metabolic pathways like iron and sulfur cycling. So Mars is very iron rich, as you can see from its red color. There's also a lot of sulfur on the surface and in the rocks. And so it is potentially possible that microbes that existed on Mars in the past or present could have these alternative metabolic pathways that are cycling sulfur or iron. Which leads us to the ultimate question of, if there is life on Mars or was life on Mars, how are we actually going to detect this stuff? Can we detect it from orbit? How could we detect it from orbit? What would we be looking for? And what about on the surface? What would we find on the surface that would tell us there was ever anything there or is something there? And detection limits, what is our limit for saying, yes, this is definitely something here, this is a signal that we want to dive more into? So I believe that is it for this. So I want to keep it short and sweet.
Okay, so we have plenty of times for questions if anybody has any about the warm-up talk in particular.
Yeah.
You mentioned ice volcanism possibly on Pluto. Mm-hmm. What's the source of that? What causes the volcanism?
So that one would be something like, there it is, something like warmer ice at depth. So it's not necessarily liquid water, but warmer ice would be less dense and would rise up to the surface.
Oh, it's as simple as that? You
Yeah.
don't get any compressional, like we see on some of the moons?
Possibly, but this is all very, very new data, so I'm sure modeling has possibly already started, but there's no good results of that yet.
Okay.
So yeah, but it could be as simple as just at depth it's warmer and less dense and then rises up. So.
Somebody else over here, yeah.
So my question's pretty simple. What about Mercury, if we're talking about the solar system?
What about it? I
mean, just, I come from astronomy and earth science, so planetary science to me is totally different. So I guess my question is really about Venus too, so Venus is rough to send a mission to, but there hasn't really been a lot of work done on trying to figure out Venus for the last 20 years or so. So I guess my question is, why do Venus and Mercury not mentioned here, I guess?
Well, for this talk in particular, I was just going to focus on the things that we're covering in the sessions later. But for astrobiologically speaking, Mercury is too close, really, to the sun, so it's not really in that habitable zone. So for astrobiological research, it's just too hot. So too hot to have liquid water stable on the surface, and liquid water right now is our kind of thing that we're fixated on. So you could argue that maybe there's some other thing there that would be supporting of life, but for NASA's current astrobiology research, it's all about the water.
Other questions?
I guess this is more of a general comment, but I still don't know why we still try to define the habitable zone based on water at the surface. It seems like
Yeah.
like something we should move away from.
I totally agree.
I don't know why NASA. Maybe it's because it's detectable at long range, maybe more easily, but it has the concept of a habitable zone. To me, is outdated and needs to be revised
Absolutely.
based
And-
on what we know about Earth and vent systems, and Europe is going to be way outside the habitable zone. And
Yep.
anyway, just a thought.
Yeah. It's very true. It's an overly simplified thing that they're using as a key variable. So yeah. I suppose you have to start somewhere.
Any other questions? If there aren't, we'll go ahead and move on to the first science talk.